okay with it. Colin, thanks very much. I love the lot there, and it's fascinating that the scale is just perfect, isn't it? Yep. That last curve is beautiful. It's the right scale. Is that the first time that's been shown theoretically? I know other people have worked on similar models in the past, but is that the first time those scales have come out and that kind of spiral structure has come out in this model?
Well, I was stunned when I got that.
It looks stunning, I agree. Beautiful.
But no referee has found it stunning.
Really? You need some better referees.
I do. I need a cohort of enthusiasts to go out and sell the theory.
One thing, Colin. Isn't the shape of these things kind of Keplerian as it comes of the rotation curve, kind of Keplerian to begin with, and then flat afterwards? So not rotating like a plate, rotating like a solar system for the inner.
No, it's pretty much plate-like rotation when you're right in the center. It's very, very strongly controlled by the rotating mass. And so what you're seeing is that inertial frame rotating. It isn't it doesn't seem rotating to itself, but that's the motion, the motion that you're most seeing. So I think that's right.
Our friend in Australia, for whom it is now about 3 a.m. in the morning, is not with us at the moment, but did look at your previous talk and sent a couple of questions through. One of them was on the rotational measurement of the galaxy. There's luminous matter in the middle, and the rotation curves that you're showing extend out way beyond the edge of the visible edge of the universe. It's about twice as far. Do you know how those things are measured? How the rotational profile is measured?
Well, I think you look for a galaxy that you see edge on, and you put a slit up, the slit up, and you just look along the slit and look to see the redshift. I think so. I don't know.
Okay, right, good.
It's just redshift, yes.
Okay, good.
Can I?
Any other questions, Peter?
Yeah, I don't know whether you've seen my talk on this. One of my talks on this network on dark energy, because in that I have a relationship with the Sharma theory of Mark's principle and the dark energy, and that also includes redshift, the cosmological redshift. So I think you might have a look at that, because it could be that we are looking at different sides of the same problem.
So what are you looking? Dark energy, in my mind, is just the curvature of space, just the curvature of the universe.
Well, I don't think it's anything to do with curvature, because the universe is no. If you look at the talk, what I'm trying to do is say that I believe there's a critical value for dark energy, which is 2/3 of the energy of the universe. Right. If it's 2/3 of the energy of the universe, then in fact that gives a direct, simple relationship between redshift and the acceleration term. They're not unrelated; they're related. So the redshift velocity comes from the acceleration term.
Well, it does in any standard model, in any model. I mean, the model I'm using, de Sitter space, the dark energy is just the constant in, and it's just a sphere.
Well, just have a look to see what I've done. Because,
I will, yes, I will.
Because further on, I go to show it's the same as if you'd used Sharma's theory, and then adapted it for the particular case, used Sharma's theory, using gravitomagnetism and all that, and you get the same equation as if you'd used that.
Right. No, I will. I'm very interested in that. So, can you send me a link to make sure I get it?
Yeah, it's on the Google website. On the Quicycle.
On the meeting site.
If you go to Quicycle.com, and look for Peter's most recent talk, it's that one.
Okay.
Arnie,
okay, I'll do it.
You'll pick it up.
You don't have to find it.
I mean,
it's on YouTube, so you pick it up from YouTube.
It may be that we could get some sort of common connection on that.
Okay.
I have a question of a non-practitioner. I'm not a general relativist. I'm not a cosmologist coming from the particle physics, nuclear physics, etc. But I have a simple question, maybe for general question about this. Is general relativity compatible with the Keplerian orbits? To my mind, when I hear about the general relativity and we still talk about the Keplerian orbits around Newton, because Newton's themes could prove the Kepler's laws. And if Newton's laws are not, Newton's mechanics is not correct, how correct are we talking about the Keplerian laws basically? And then how does general relativity account for this? This is not pertinent to this talk perhaps, but I just thought that I'll throw open this question because always we hear this, Keplerian orbits. In general relativity, people also, cosmologists have to talk about it, but are they consistent?
For most purposes, Keplerian orbits are pretty good. It's only when you're very close to a very heavy object that they're not good. In fact, some of the terms in the Schwarzschild field come out the same, and the Schwarzschild metric come out the same as Newtonian. Formula for angular momentum, I think, example.
One other question, Colin. You're considering we have a black hole at the center of the of each of the galaxies, and that's rotating.
Yes.
And that's producing, and with a large angular momentum and a large rotation, different one for each galaxies, but they're all pretty big, and you have slightly different levels of the asymptote. Does that thing have to be a black hole?
Well,
any large
we just assume it's a black hole. That's all. It doesn't have to be, but it's something like 10 to the 11th or 10 to the 12th solar masses is big. It's very big. Sagittarius A star, by the way, is not the center of our galaxy.
Is it
it's about halfway, not the center of the galaxy, only 10 to the 6th. It's a baby, it's nothing. It's tiny. Okay. Have a look at my book, because I've got some pictures. If I get a chance, I'll put some pictures up, but completely demolish the Sagittarius A star being the center of the galaxy.
Oh, right. So how far is the proper center of rotation?
About twice as far. It's about twice as far. About twice as far.
Twice as far as what?
As Sagittarius A star. So it's about 9 kiloparsecs rather than 4.6 or 4.5.
Okay, thank you. Interesting. I'll look at the book.
I could go through that. That's a completely different. I've not got it prepared. I could do it from the book, but can we do later
one?
Yeah.
Is it a lot? Is it an hour or is it 10 minutes?
What? The Sagittarius A star. Oh, it's about 10 minutes. Maybe we get time today. But let's keep going.
Well, we have a series of short talks as well, so we can do that, just a few of us, and stick it up there as well if you like. If you'd like to do that.
I'm delighted to talk about this anytime you like.
Okay, right. We'll organise a short one for you then. That's good. Great. Any more questions on this bit? We let Colin get on with quasars.
Yeah, I just have a couple of Colin's general questions. I really like the references to Shyama's work because I think it's very important. But I just have a couple of general questions. One is, you're looking at galaxies like from the outside. Shyama's work, I believe, is most pertinent for explaining inertia. And that means we're looking at all of the galaxies in some sort of a large total concept, rather than kind of looking down on a galaxy. We're looking out from our point of view at everything. Is there symmetries that could be applied to our view of not just of the whole universe, all the galaxies together, rather than when you look down on something, you see things rotating? So that's kind of one question, whether you have any ideas to how to translate your work into the framework of what we're seeing, which is a world around us that is pretty symmetric. rather than, you know, I don't see any spirals or so of the whole. I don't know if I'm making sense at this point, but the second one, the second question I have is, by the time we start using normal gravitational theory for things as large as a galaxy, you know, we have, you know, 50,000 light years or so, can you make any comment about the speed of gravitation? Because if gravitation is not instantaneous, would that not also affect the calculations that you've just done? Is there some comment you can make about the speed of gravitation?
Well, I assume that the inertial drag effect is a gravitational disturbance caused by rotating matter, and therefore it's propagating at the speed of light. It's a disturbance to the background fields, so it's being propagated at the speed of light.
Okay,
so
but there's no you know, retro term in your equations. There's no, you know, when you get to something that big, shouldn't you be calculating the time it takes for the influences to get to? I mean, you're talking about 50,000 light years. You're talking 50,000 years of propagation.
It's an instant in the life of a galaxy. I think you're trying to boggle your mind with big numbers. It all scales up.
I think if the galaxy's been rotating for 50,000 light years, and let's hope it has, if you take, I think you're talking about looking at the retarded solutions of
retarded solutions. Yeah, right. I mean, I just wondered, you know, at that scale, unless you're assuming gravity moves at infinite, which a lot of people do. If you're assuming it's moving at light, should those equations not include a retarded potentials?
I suppose they should, but
I think they should indeed. But if they're traveling at the speed of light, but you're quite right, Wolf, in saying that it's not entirely certain that gravity is not instantaneous in this respect. But either way, if you had a constant rotation, it doesn't matter, because although the influence will be coming from 50,000 years ago, the frame dragging is still, even if it's traveling at the speed of light, then propagating outward constantly. So it should make no difference, I think, to the solution, provided unless there is a variation in the rotation of the object at the center. And it's going to be pretty hard if it is 10 to 12 solar masses. It's going to be pretty hard to speed it up or slow it down. So I guess I presume the thing's been rotating like that for some time.
Yeah, I think that's the right way to think of it.
Yeah. Yeah.
Okay, shall I soldier on?
I had one point related to what I was talking about a week ago, or maybe it was two. If you take a very simple experiment, like they show in classical physics, of two rocket ships going off in opposite directions, right? One of them from one inertial reference frame, the first, and then one from the second one. There should be total symmetry in the two. But if you have the rocket ship giving off an exhaust, where the mass is going in the opposite direction, then the inertial reference frame changes. So it seemed to me that the inertial reference frame is totally a function of the gravity of all the objects in the space, and it would be relative, like I think you're saying, right? So have you considered the simple model of the two rocket ships, one with an exhaust, one without? You can't do it without, so it seems like in classical science fiction videos, right, the person who leaves and then comes back is much younger than the person who stayed stationary. But the only thing that differentiates the two is the exhaust from the rocket ship that left and came back. And so if you add up all the gravitation from the exhaust of that rocket, you totally explain the inertial reference frame and why there's a difference in aging between the two situations. Does that make sense?
I guess so.
So I guess it's consistent with what you're saying.
I think I'm saying something much simpler. Anyway.
In your case, I thought the inertial reference frame of each galaxy is somewhat separate, because most of the mass is in the area of the galaxy. And that would be consistent with all the mass of that galaxy having a much bigger influence on the inertial reference frame than the galaxies that are much further away.
Well, I guess that's right. That must be right. Yeah,
Yeah, that must be correct. Lyndon, you had a question.
Yeah, I may have remembered this wrong, but I thought the arms, you have the beautiful diagram of the arms of the galaxy and showing how it matched the picture. If I remember rightly, the arms are spiraling inwards with time. Is your model time dependent?
no, the arms are moving outwards. They're not spiraling it. They're not moving in. It's like a Catherine wheel. The stars are moving outwards along the arms. You've got matter being ejected from the center, and it's condensing into stars and so on.
Okay.
And that's
I must have remembered wrong.
I think what Lyndon's referring to is what you said in your previous talk, that the spirals come inwards and towards each other, not absolutely.
Oh yes, yes. The pitch of the spirals is going towards flat as you go out.
That's right.
Flattening out.
How will it develop in the future with your model, with time?
Well, it's constant. It's static. It always looks the same.
Okay.
It's a static model.
That's fine. Okay. Just only wanted to know about
that. Colin, is there any observational evidence that galaxy shapes are static over long periods of time and that they don't change shape? Or is it just
isn't. I could not possibly observe that long.
Right.
It's just common sense, though.
Well, I mean, there are galaxies that seem to be in different stages of maturity in terms of the spiral. Some that have one more twisted up, some that looks like Hoag's object, which are almost completely toroidally symmetrical.
Yes.
Well,
yes. I'm just modeling classical spiral galaxies. That's all.
Okay, gentlemen, I think perhaps we should move on and get the second part of Colin's talk. But that is also up to Colin because it's now 6:20. We're a bit later than we expected to be at this point. Colin, does this fit in with your plans for later this evening? Can you manage to give the second part?
I'm fine till 7 o'clock. I'm fine till 7 o'clock, John.
And
I'll go and consult the cook.
That is only
the cook's no longer within hailing distance because I had to move computers.
Remember, we want a question and answer as well. So is there enough time for both that and the Q&A?
Yes.
Good man, go for it.